Fossils up as a screensaver because I'm not going to show any pictures of fossils for the rest of the talk. This is Complexity, Diversity in Early Land Plants. My co-author is Karl Niklas. And as you know, the history of life is replete with unpredictable variables or contingencies. So, does this mean that there are no patterns or directions, real or detectable in the course of evolution, that relate to the relationships among these factors? Now, some people may say this is philosophical, and certainly Nick Shea has written about it. Farrell, we've done some interesting things. Initially, I didn't like it, but then I sort of got interested. So, what are the questions motivating our study? Can we detect, can a well-delineated phylogenetic structure be ascertained for early vascular land plants? I don't mean to offend anyone in this, because there's been a lot of really excellent people working on phylogenies in early land plants. But we took a slightly different approach, as I'll talk about in a minute. Is there any evidence that complexity has changed over the course of early vascular plant evolution? That's sort of the heart of it. We have to define complexity. I'll get to that in a minute. And by early, I mean Silurian, Devonian, but we have a few exceptions there as well. Well, then what do we mean by complexity? This has been debated. It could be subjective. Numerous definitions have been advanced. Again, McShay has done a pretty good job laying some out. We have to have complexity defined in a way we can translate it into characters, the way I see it. Most workers agree the concept is vague. Karl threw in that perhaps indefensible. That wasn't my idea. Okay, especially since there are numerous examples of reductive evolution. There you go. Sure. Complexity, we all think, increases, but there's clearly some cases of reduction. So how does that all figure? All right. For our purposes, we're going to define complexity as any increase in one or more of the following. And this sort of follows McShay. We modified a little. The number of body parts, the number of different body parts, the ordering or arrangement of body parts, and the functional integration of body parts. And we'll get to complexity in a minute, but as to the phylogeny, again, we realized we had to have a comprehensive phylogeny. There really wasn't any that didn't include modern plants. We had our own philosophy about how to do a phylogeny. We restricted it to fossils only, used modern plants. You get missing characters which have a deleterious effect. So we set out to do our own analysis, perhaps foolishly so. Now, so selecting taxa, we selected the best preserved examples of important Silurian, Devonian taxa, genera for which fewest phenotypic diagnostic characters are missing. Again, we wanted to reduce the number of missing characters in our analysis. We selected taxa traditionally considered to be the most representative of their major lineages, Rhynia, Phyton, etc. We also added some evolutionary or phylogenetically important taxa, some of which are carboniferous. We slipped over the border. We even added Equisetum. All right. For characters, and I'm not going to go through our character matrix now, it's going to be published soon enough, but we exploited new characters embedded in traditional characters. We also used characters generally used. And the number and location of protoxylem points and their disposition in the procambium is one example of the kind of things we look for. We follow traditional definitions for important characters, following Esau carefully. With the phylogeny, so we get to the phylogeny, we used 36 Paleozoic tracheophytes and a few later ones, and Equisetum. We had a topology, well, we had four most parsimonious trees and a well-reserved combination thereof. The new consensus tree, 4 most parsimonious trees, 36 fossil taxa, and Equisetum rooted with Agriophyton, retain the most of the zoology of the previous tree. I say that because we had a couple iterations that critics and reviewers went back and forth with us on. It was retained if we used Cooksonia at the base. Both tree topology resonated with classical Banksian phylogeny in a sense, as you'll see. Equisetum nests with the sphenophytes, no surprise there. Okay, the rhinophytes in green, the zostrophyllophytes in blue, and in pink, the trimerophytes with the sphenophytes in gray at the bottom. Let's see if I can find this green thing. Yeah, there we go. This was our previous tree we published earlier. We cleaned it up some. We got some nice comments from our colleagues. There were some publications of papers that revealed some new characters, and so we modified it. You'll notice that it's better resolved up here at the end of the trimerophyte lineage and also in the zostrophyll. So it's a pretty clean tree, and it was very hard to destroy this tree. Not that we believe any particular trees, these are all hypotheses, but this one served our purposes in forming a template for studying the evolution of complexity, its relationship to size, its direction, directionality. All right, this is the tree again, and here we have plotted secondary growth. I don't want to dwell on it. It occurs early with Amoricophyton showing up pretty early. It also occurs in cytophyton and wound tissue. And you get a bunch of a number of taxa with secondary growth that are protostillic, and then you get eusteals up at the other end of the tree. All right, a summary of our tree and its implications before we get into the world of complexity. All trees identify two megaclades derived from the rhinophytes, zostrophyllophyte, lycophyte clade, and the trimerophyte euphylophyte clade. That's nothing new. The topologies of both trees are similar. I told you we recoded some of the things. We looked over it carefully. We benefited from criticisms and suggestions of our colleagues. The sequence of branches consisting of euphylophytes identified the progymnosperms as paraphyletic. Didn't surprise us, but it may not go down generally speaking. The seed, what you call a seed can vary. It's a subjective concept at some level, but it appeared several times according to some definitions. And as I said, secondary growth appears early in the trimerophyte euphylophyte clade and appears in several groups in different configurations. All right. What about the tempo and mode of the appearance of complexity? Recall that complexity I just defined a few minutes ago based on 4 criteria: number of body parts, how they're arranged, the extent to which they are functionally specialized or diversified, the extent to which they are functionally integrated. All these features, importantly, are codified in the character matrices of our phylogenetic analysis. In other words, you have to have some kind of character matrix that reveals a change to more complexity in those categories, which we did. And I don't want to get into this now because of time, but you know, increasing number of body parts, arrangement of body parts, and their examples. Specialization of tissue systems has to be to some extent inferred from the arrangement of organs and well, especially the integration of body parts. All right, the appearance, I'm going pretty quickly today. So the appearance of, that's not unusual, the appearance of derived character states in the new tree, juxtaposed with their first recorded appearances in the fossil record, indicates a complexity increase throughout the Silurian Devonian time interval, and that the trend was attended by increasing size with a well-defined zostrophyllophyte lycophyte clade and a well-defined trimerophyte euphylophyte clade. And we plotted it out, and the R squares support this. They support cumulative number of new derived characters increasing with age. Log diameter, we were interested in increasing complexity in its relationship to size. Log diameter versus age was positively correlated. And cumulative numbers of new derived characters against diameter was correlated, so size and complexity, the way we defined it, seemed to be correlated nicely. Interestingly, man, it's drying here. The cumulative number of derived characters over time increases dramatically early on and then plateaus. So, plateaus by the late Devonian, yet the fossil record shows that the number of species continues to increase throughout the Paleozoic. So what do we ascribe to that? Well, either we failed to identify enough characters, or the characters that had already evolved in recombination could produce the diversity in species that we see later. So we suggest that speciation after the Devonian involved permutations of derived character states that evolved by the end of the Devonian, which resonates with the concept of modularity as advocated by Farrell, certainly. In other words, you have a certain number of things, you can recombine them. Some of them are impossible recombinations, but many aren't. And toward the middle and end of the Devonian, you got a recombination of characters that were, or characteristics that had already evolved. That is not to say nothing new evolved after that, but it's interesting. Another thing that was interesting is if we took subsets of the characters that produced the tree to see how much resolution we got, and it shows that at least, again, it's criticizable, but if you remove the reproductive characters or you remove the anatomical morphological characters from the matrix, you get different results. And certainly early radiation is characterized by anatomical and vegetative morphological innovations rather than reproductive ones. This goes against my sort of core belief system for flowering plants, but it certainly might have been true in the early stages of vascular plant evolution, where most plants had spores, and they were homosporous than heterosporous, but not much different. In a sense, there wasn't much radiation of reproductive characters in that interval, or we are missing critical reproductive characters along that interval because we have an imperfect preservation of such things as gametophytes. And if you look at the comparison of the trees, this is the same analysis, having removed all reproductive characters, and it's reasonably consistent with the overall tree. This is the same analysis without vegetative characters. So either there was convergence, massive convergence in reproductive structures, or there wasn't much diversification of reproductive structures during that interval. So, in conclusion, the taxa sample segregated into two major trachophytes, superclades, trimerophyte euphylophyte clade, and a zostrophyllophyte lycophyte clade. That's nothing new. I mean, that goes back to the Banksian paradigm. Complexity computed on the basis of emergent character states and body size increased within each of the two clades, although at different tempos. The lycopsids got there earlier, and there's a lot of convergence in the characters that developed within that lineage. Substantial, as I just said, substantial convergence is evident, leaves, vascular camera roots, etc. Then conclusions 2, arborescence occurs for the first time in the lignophyte, calmophyton clade in two forms, obtaining the arborescent habit: the development of a vascular cambium or the proliferation of an anastomosing primary xylem network. And our analysis indicates that innovations can be recycled or remixed, as in the case of secondary growth in the vascular cambium, and that such a remixing was important in early vascular plant diversification. And I think that's it.